Alright, so we now consider or again, I'm going to discuss with you the calculations of ATP from the lipid oxidation because it is very important that you're able to grasp and understand exactly how ATP is calculated from the oxidation of fatty acids. As you might have noticed in your previous examination, the calculation of energy yield or the determination of energy yield from different fuels, different energy sources, different molecules is crucial in our study of metabolism. Okay, so this I discussed this with you in an earlier previously shared lecture video, but I will again discuss this with you just to emphasize some points. First and foremost, you have to realize that the amount of energy or the energy yield from the oxidation of fatty acids is much greater than the energy yield from the oxidation of glucose. On a per gram basis, the difference is very significant. We attribute this to the fact that the fatty acids consist of a number of carbon-hydrogen bonds. Carbon-hydrogen bonds have high energy. It's the reduced form. It's a reduced bond, right? When I speak of reduced bonds, I speak of atoms that have high electron density. So a carbon atom that is bonded to hydrogens are in a state of relatively high energy electron density. So you can think of the fatty acid, the chain fatty acid tail, as being reduced. It's in a reduced state. And therefore, its oxidation will naturally give rise to much greater amount of energy, say for example, compared to glucose, in which case the carbon, if you're going to remember the structure of glucose, the carbon atoms in glucose, except for carbon number one, are all bonded to oxygen, right? And therefore, all bonded to oxygen in the form of hydroxyl group. Carbon number one is even more oxidized because it's doubly bonded to oxygen. The point that I'm trying to make is that the carbon atoms in glucose are definitely in a more oxidized state, and therefore low electron density, which translates to, well, lower chemical energy content compared to the carbon atoms in fatty acids, specifically the fatty acid tail or the chain, in which case there's a lot of carbon-hydrogen bonds. Okay, so the first thing that we have to ask ourselves is how is it or how do we utilize fatty acids as energy source? Remember, fatty acids are primarily stored in the form of triacylglycerols, or as we also prefer to call it, triglycerides. Triglycerides are stored, or rather are found in adipose tissues. So the first thing that we have to do in using fats as energy source, or fatty acids as energy source, would be the mobilization of fats, mobilization of triacylglycerol or triglyceride. So from the adipose tissues, it is delivered to the muscles or to other tissues, peripheral tissues that are in need of fatty acids as energy source. Okay, under what conditions might that be? We're going to discuss that in future discussions. For now, let's focus on the utilization of fatty acids itself. Okay, so the triglycerides are going to be delivered to the muscle, for example, or to the peripheral tissue that is in need of fatty acid as energy source. What's going to happen is that the triacylglycerol, as you can see in this figure, will be acted upon by lipases. Lipases are enzymes that hydrolyze triacylglycerol, specifically the ester linkages of the triacylglycerol, into the corresponding free fatty acids and glycerol. Okay, so we have free fatty acid, free fatty acid, free fatty acid. So three fatty acid molecules are going to be liberated from triacylglycerol, plus of course the molecule of glycerol. Now, it has to be mentioned that free fatty acids can also be obtained from phospholipids. Remember, structure of phospholipids, we've studied this a while back. Phospholipids consist of a glycerol molecule and two fatty acids, as well as a phosphate group in the polar molecule. So phospholipids can also serve as a source of fatty acids for oxidation, right? The thing that you have to bear in mind, though, is that unlike lipases, we actually have different kind. We have, unlike lipases, that act on just ester bonds in triacylglycerol. Phospholipases may act on ester bonds in phospholipids, or they may act on phosphoester bonds in phospholipids. What am I talking about? So here, phospholipases catalyze hydrolysis of bonds between fatty acids and the rest of phosphoacylglycerol. So for example, you have here A1, phospholipase A1, which cleaves the bond between the fatty acid that is linked to the terminal carbon in glycerol. Alright, so it cleaves the bond, the ester bond, between the fatty acid and the hydroxyl group of glycerol found in its terminal carbon. You also have phospholipase A2, which cleaves the ester bond between the fatty acid, or between a fatty acid and the hydroxyl group that is found at the internal carbon of glycerol. You have to differentiate that phospholipase from phospholipase C, which cleaves the bond between the oxygen atom and the phosphate group. Alright, so this phospholipase specifically cleaves a phosphoester bond. Now, phospholipase cleaves a phosphoester bond between the phosphate group and the polar group of the phospholipids. Okay, so whereas the lipases just cleave ester bonds, the phospholipases cleave ester and phosphoester bonds. Okay. Now, in any case, what we're interested to know is the fate of the fatty acid. So let's look at that. The fatty acid, which is released from the action of lipases and phospholipases, have to be activated. When we speak of activation, we think of it as remember the energy investment phase in glycolysis? That is similar here. We have to activate the fatty acid. Remember, it exists in the form of its carboxylate. In that form, it's not very active, and so will not be able to force it into undergoing a reaction, unless, of course, we transform it into a more reactive metabolite, which is exactly what we're going to do, or what the body is going to do. So the fatty acid is activated into fatty acyl-CoA, right? So you can think of acetyl-CoA. Acetyl-CoA is can think of acetyl-CoA as the molecule that is produced from the thioesterification reaction between acetic acid and coenzyme A. So when you speak of fatty acyl-CoA, it's the molecule that is produced from the thioesterification reaction between fatty acid and the coenzyme A. right? So fatty acyl-CoA, it's the activated form of the fatty acid. So let's look at that. Fatty acid, as I mentioned, fatty acid oxidation begins with the activation, right? We were transforming it from a relatively inert um, uh, metabolite into a more reactive one. So in this process, a thioester bond is formed between the carboxyl group of the fatty acid and the thiol of the coenzyme A. So you see here, in step 1, this is catalyzed by a fatty acyl-CoA synthetase. In step 1, a molecule of ATP reacts with the carboxylate in the process, releasing pyrophosphate. Now, this pyrophosphate actually consists of two molecules of phosphate, consists of two phosphate groups that are covalently linked to each other. These are not individual inorganic phosphates. Pyrophosphate are linked by phosphoanhydride bonds. Okay, so we're going to go back to that later because that's going to be important in ATP calculation. So the carboxylate reacts with ATP to, in the process, produce acyl adenylate intermediate. So in this case, it's actually the oxygen of the of the carboxylate group, the negatively charged oxygen of the carboxylate group that acts as a nucleophile, displacing the pyrophosphate and forming a bond with the internal phosphate of ATP. So you end up with AMP acyl group, or the acyl adenylate intermediate, fatty acyl adenylate intermediate. Now, the fatty acyl adenylate intermediate will then react with coenzyme A. So this time around, the coenzyme A, using its sulfur atom as the nucleophile, will attack the carbon, this carbon atom, and this carbon atom will undergo nucleophilic acyl substitution reaction to produce a thioester, right? Thioester. Remember, thioesters are just esters with the oxygen replaced by sulfur. This is very active, okay? So you produce a thioester. It's an activated acyl group. So the overall reaction entails the reaction between carboxylate, ATP, and coenzyme A to produce fatty acyl-CoA, AMP, and pyrophosphate. So how many molecules of ATP are consumed in this case? One molecule of ATP. But, as we're going to note later, it's actually equivalent to two molecules of ATP. Why? Well, we're going to revisit that later. For now that we have the fatty acyl-CoA, it's the activated form of the fatty acid, in the cytosol, we need to be able to deliver it into the mitochondrial matrix. But the problem with the mitochondria, again, is that it's very selective in terms of the molecules that it allows to pass through it. Well, the inner mitochondrial membrane, that is, because the outer mitochondrial membrane is permeable to almost any molecule, any metabolite. So the acyl-CoA crosses the outer mitochondrial membrane, as expected, but not the inner mitochondrial membrane. So how do we deliver the fatty acyl-CoA into the mitochondrial matrix in that case? Remember, beta oxidation, the oxidation of fatty acids occur in the mitochondrial matrix. So the acyl group is then transferred to carnitine. Then the carnitine, the fatty acyl carnitine, is transported across the inner mitochondrial membrane by a transport protein. Okay. Once inside, the fatty acyl carnitine reacts with the coenzyme A in the mitochondrial matrix, regenerating a molecule of fatty acyl-CoA and carnitine. Now, the enzyme that accomplishes this is the carnitine palmitoyl transferase, which has a specificity for fatty acyl-CoA that has carbon atoms ranging from 14 to 18 carbon atoms long. Okay, so let's look at this diagram. So as I mentioned, the fatty acyl-CoA in the cytosol can freely enter, can penetrate the outer mitochondrial membrane, so it's able to access the intermembrane space. The fatty acyl-CoA will react with the molecule of carnitine. Look at the structure of carnitine, right? It has carnitine. It has a hydroxyl group, all right, at carbon number 1, 2, 3. All right, I'm sorry, carbon number 2. I'm referring to carbon number. Well, actually, this is 1, 2, 3, 4. Carbon number 3. At carbon number 3, the hydroxyl group of carbon number 3 will act as a nucleophile. It's going to displace the coenzyme A group upon its reaction with the fatty acyl CoA, producing fatty acyl carnitine. And of course, displacing the coenzyme A, right? Displacing the coenzyme A. Now, the displaced coenzyme A will simply diffuse back into the cytosol. What about the fatty acyl carnitine? This fatty acyl carnitine will be transported to the mitochondrial matrix. Why? Because of a transport protein. There is a gate or protein that allows the transport, allows fatty acyl carnitine to cross the inner mitochondrial membrane. Again, do not forget the enzyme that catalyzes the reaction between carnitine and the fatty acyl group is carnitine acyl transferase. Okay, so once inside the mitochondrial matrix, a molecule of coenzyme A in the mitochondrial matrix will undergo nucleophilic acyl substitution reaction with fatty acyl carnitine, in the process displacing carnitine and regenerating a molecule of fatty acyl CoA, right? This is going to be oxidized in the process of beta oxidation, going to serve as a source of energy. Now, carnitine will be regenerated as well, and it can cross the inner mitochondrial membrane back into the intermembrane space, right? And the process happens again, right? You can think of it as a shuttle system that allows the transport of fatty acyl CoA from the cytosol to the mitochondrial matrix. Okay, now beta oxidation, as I mentioned, it's the process that oxidizes fatty acids to carbon dioxide. Okay, now beta oxidation of fatty acid, of course, is an aerobic process in the sense that the reduced equivalents as well as the acetyl CoA that is generated from the oxidation is oxidized in are oxidized in the allocrine transport chain and in the citric acid cycle. Okay, so beta oxidation is a series of reactions that cleaves carbon atoms two at a time from the carboxyl end of a fatty acid. So the complete cycle of one beta oxidation requires 4 enzymes. Reaction 1 is actually the introduction of a double bond at the alpha and the beta carbon, right? The oxidation of the alpha beta carbon-carbon single bond to a carbon-carbon double bond. It's a dehydrogenase that accomplishes that oxidation. Reaction 2 involves the nucleophilic addition reaction. It's a conjugate addition reaction. It involves the hydration of the carbon-carbon double bond into a beta hydroxy thioester. Reaction 3 involves the oxidation of the beta hydroxyl group to a ketone or to a carbonyl group. And reaction 4 involves the reverse Claisen condensation. Claisen condensation is a reaction that you learned about in organic chemistry. So the reverse Claisen condensation has a net result of releasing acetyl CoA and a fatty acyl CoA that has been shortened by 2 carbon atoms. Okay, let's look at the diagram, exactly what's going on. So I want you to look at this fatty acyl CoA, right? This is your carbonyl carbon of the ester, the thiester. This is the alpha carbon and the beta carbon. So what's going to happen first is that the fatty acyl-CoA will be oxidized by acyl-CoA or fatty acyl-CoA dehydrogenase. In the process, generating a double bond between the alpha and the beta carbon. Okay, notice that the fatty acyl-CoA has the fatty acyl-CoA dehydrogenase rather uses FAT as a coenzyme, right? Process generating FADH2. Okay, now this FADH2 will of course be oxidized in the electron transfer chain, but more about that in a moment. So the product that is produced, alpha beta unsaturated thiester, will undergo hydration reaction, the nucleophilic addition reaction, right? This is going to be catalyzed by inyl-CoA hydratase. A molecule of water will attack the beta carbon. In the process, you end up with the addition of the elements of water across the carbon-carbon double bond. So you end up with a hydrogen at the alpha carbon and the hydroxyl group at the beta carbon. So what is this? Beta hydroxy thioester. Okay. Now, the next step is an oxidation reaction again, in which case the hydroxyl group will be oxidized into a carbonyl group. So you end up with L-hydroxyacyl-CoA dehydrogenase oxidizing the molecule into a beta-ketoacyl-CoA. Now, I want you to remember that, I want you to notice rather, that this reaction involves the production of NADH. Okay? Now, the next step would be a reverse Claisen condensation, in which case another molecule of coenzyme A will attack this beta carbon. Alright, remember the Claisen condensation back in organic chemistry? This is just the reverse. When the sulfur, the thiol group of the coenzyme A attack the beta carbon, this alpha carbon beta carbon bond will break and the alpha carbon will become protonated, in the process producing fatty acyl-CoA and of course acetyl-CoA, right? So that's one cycle, because the fatty acyl-CoA that has been shortened by 2 carbon atoms will undergo another round of beta oxidation, okay, until you end up producing acetyl-CoA. Okay, so one round of beta oxidation produces 1 acetyl-CoA, 1 shortened fatty acyl-CoA, 1 FADH2, and 1 NADH, right? If you're going to consider the case, say for example, of this molecule, what is this? 9 times 218. Now, this is stearic acid, right? Stearoyl-CoA. Now, in this case, how many rounds of beta oxidation will be necessary to completely oxidize this to acetyl-CoA? Well, it has, remember, acetyl-CoA has 2 carbon atoms, so in effect, you have 18 carbon atoms here in total. There are 9 acetyl-CoA groups that are obtainable from the beta oxidation of stearoyl-CoA. So that's going to be 18 divided by 2, that's going to be 9, right? 9 acetyl-CoA, but remember, the last beta oxidation produces 2 acetyl-CoA. So the number of beta oxidation cycles needed to oxidize stearoyl-CoA is just 18 divided by 2 equals 9 minus 1, because the last beta oxidation cycle produces 2 acetyl-CoA molecules, right? Okay, so in this case, all right, so in this case, you have, so mentioned, 18 carbons in stearoyl-CoA. It's going to require 8 beta oxidation cycles, so 8 FADH2, 8 NADH are going to be formed, and you're going to generate 9 acetyl-CoA, right? I'm not sure if I can, maybe I can write it here. So let's calculate now the number of ATP. You already know it before, so let's say here. Um, remember, we generate, we have 8 beta oxidation cycles. So we have 8 FADH2. And what is that equivalent to? It's equivalent to 8 times 1.5, right? 1.5 ATP, because 1 FADH2 is equivalent to 1.5 ATP. So 8 times 1.5, that's going to be 12 ATP. Now, what about the next? 8 NADH. 8 NADH. What is that equivalent to? 8 times 2.5, so that's going to be 16 plus 4, 20 ATP. Do you remember in the past what happens to acetyl-CoA? Acetyl-CoA is oxidized via the what? The Krebs cycle, right? One acetyl-CoA, remember, produces the oxidation of acetyl-CoA in one round of the Krebs cycle produces 3 NADH, 1 FADH2, and 1 GTP. So 3 NADH, 3 times 2.5, that's 7.5. 1 FADH2, that's 1.5. So 7.5 plus 1.5, that's going to be 9. 1 GTP is equivalent to 1 ATP, so 10. So that means how many acetyl-CoA do we have? So 9 acetyl-CoA. That's equivalent to 9 times 10, because 1 acetyl-CoA in one round of Krebs cycle it produces is equivalent to 10 ATP. So 9 times 10, 90 ATP, right? Okay, so maybe I can move this here. All right, so 9 acetyl-CoA. All right, this is the energy payoff phase, right? But what about the energy investment phase? Earlier, one molecule of the fatty acid is associated with one molecule of ATP for activation, right? So minus 1 ATP that is used for activation. But this is actually equivalent to how many ATP? Well, all right, let's go back to that diagram because I mentioned earlier that it's going to be consequential in our later discussion. So here, remember here, this is the ATP molecule that I am talking about, reacted with the carboxylate to produce the fatty acyl adenylate intermediate. All right, now the interesting thing here is that you produce a pyrophosphate. What did I mention about the pyrophosphate earlier? It's two phosphate groups that are linked to each other. Now this pyrophosphate actually is going to be hydrolyzed to two inorganic phosphates. So that's going to amount to another phosphodiester, another phosphoanhydride bond that's going to be hydrolyzed. So in that case, if there's another phosphoanhydride bond that's going to be hydrolyzed, how many phosphoanhydride bonds have we cleaved here? Well, one in the production of the fatty acyl adenylate intermediate, and another one when the phosphoanhydride bond in the pyrophosphate is cleaved to produce inorganic phosphates, two inorganic phosphates. So that means that yes, we've consumed one ATP, but formally we have actually used up 2 ATPs because why am I so here? We've formally used up 2 ATP molecules because we have broken 2 high energy phosphoanhydride bonds, so minus 2 ATP. So the total, let's see, total would be 12 plus 20 plus 90, so that's going to be 32 plus 90, 122 minus 2, that's going to be 120 ATP molecules, right? 120 molecules of ATP from one stearic acid molecule. Now, this is clearly much greater than the amount we obtain from one glucose. Remember, assuming that we're talking about muscle and brain, muscle and brain, right, uses the glycerophosphate shuttle system. So that's going to give rise to, um, let's specify it here. So here is for stearic acid. Stearic acid. Okay. If you have glucose, let's specify that this is glucose in the say muscle, okay, or brain. This is actually going to give rise to a total of 30 ATP, right? So if you're going to compare that, one stearic acid, 120 compared to glucose in the muscle or brain, 30, that's 120 over 30, that's 4 times greater. But remember, one triacylglycerol molecule actually consists of 3 fatty acids. So assuming that all of these are stearic acid, then that's going to be how many times? 4 times 3, 12 times. 12 times greater. And we're not including yet the amount of ATP that we can obtain from the oxidation of glycerol, because glycerol itself can be oxidized to glyceraldehyde 3-phosphate, which will then undergo glycolysis and then transformed into acetyl-CoA, right? See that? So the fact that there is a large amount of energy that we can obtain potentially from fatty acids, yet the body did not choose fats as the main energy source is very curious. It's very interesting, right? Why was it the case that the body in the core, living organisms in the course of, at least mammals, in the course of evolution, um, chose glucose instead of fatty acids or fats as the main source of energy? Now, the reason for that is the fact that the oxidation of fatty acids lead to the formation of ketone bodies. And ketone bodies are molecules that lower the pH of aqueous systems. So the preference for glucose is attributed to that reason, among other things, all right? Because the utilization of fats will lead to the decrease in pH to abnormally low levels that can be deadly. Okay, we're going to revisit that idea or that concept again when we talk about the regulation and the glucose tolerance curves, right? What happens when people go on a fast, etc. But that's one of the primary reasons, among other things, of course. Okay, so it is crucial that you're able to calculate ATP yields from fatty acids and from other molecules, because it informs us of the amount of energy that can, in principle, be obtained from fuels and food sources, etc. Okay? Alright, so as you have encountered in the previous exam, you were asked to calculate ATP. You will be asked to calculate ATP again in in future quizzes or exams. But the more important reason for you for studying this is to be able to appreciate exactly the differences in the amount of energy that one can obtain from different molecules and be able to apply it to understanding the metabolic consequences, right, of utilizing a certain kind of molecule as fuel. Okay, I hope that is clear. Of course, the amount of ATP yield from odd numbered fatty acids will be different, and I invite you to study that on your own. Now that I've already discussed the catabolism of even-numbered fatty acid, the catabolism of odd-numbered fatty acid will be relatively straightforward. Interesting, but straightforward. Now, one thing that you have to bear in mind is, what if there's already a double bond? If there's already a double bond in the molecule, then that means you will bypass this step, the acyl-CoA dehydrogenase step. So that means that you're just going to subtract one FADH2 from your calculations, right? Because when that step is bypassed, then you end up not performing that step anymore and not yielding ATP, 1.5 ATP from FADH2 because you lose FADH2. Okay? Alright, so I hope that is clear. Alright. Okay.